Okay, it's going. So maybe let's just start recapping some of the basic proofs that we were doing last time. The example problems that we were doing last time to prove what the derivative of certain types of functions were. So, our derivative function, the definition of the derivative of the function at a point, so if f of x is continuous, then, well, I don't know how I want to say this. Let's not write it out. Let's just write the function out there. The derivative is the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. So this is the derivative of f of x at a point x naught. This is the same thing as f prime of x naught. Good with that? Mm-hmm. So some of the examples that we finished with last time, let's redo them real quick. The first one where we calculate a derivative, I think, is for a line. So really quick, let's find the derivative of a line. So if I have a line, the equation of a line looks something like f of x is equal to mx plus b, something like that, right? Or maybe you want y here. Doesn't matter how we do it. Mm-hmm. Good with that? Mm-hmm. So what should the derivative of that thing be?
M, the slope.
Should just be m, the slope, right? So let's calculate the derivative of this function. So we need to calculate the limit as x approaches x naught of f of x is going to be mx plus b minus, maybe we'll put parentheses like this, minus f of x naught, which is going to be, do parentheses, mx naught plus b, right, over x minus x naught. Good so far? Mm-hmm. Okay, distribute the negative. So we're going to have a positive b and a negative b, those go out. So we have mx minus mx naught. So I'm going to factor the m out of both those, so I'm going to get the limit as x approaches x naught of n times x minus x naught over x minus x naught. Good? Mm-hmm. Now, remember, when we're taking the limit as x approaches x naught, x is never actually equal to x naught. It just gets really close to it. You good with that? That's how we define this symbol?
Yeah.
So, this is not a 0, and this is not a 0, so we can cancel out top and bottom. So this is equal to the limit as x approaches x naught of m. What's the limit of a constant? It's just a constant, m.
So we just proved that.
So we just proved that the limit, or that the derivative of any line at any point is just the slope of the line. Right? All we knew about x naught was it was some point in R. So maybe I should have started this with something like, let f of x equal that, comma, and let x naught be any real number. Now we're going to prove that the derivative at x naught, any real number, is always an n. So f prime of x naught is equal to that, is equal to n. Good? Okay. Let's do another one. Let's find the derivative of f of x equals x squared. So we have the function f of x is equal to x squared. We're finding its derivative. Now, last time we did this, remember we drew a picture really quick, and we said really roughly f of x squared looks something like this. Right? Mm-hmm. And we know that the derivative intuitively gives us a slope. Over here, the slope of the function is negative. Over here, the slope's 0. Over here, the slope's positive. So whatever the derivative function does, it better be negative over here, it better go through 0, and it better be positive over here. Okay. So whatever our derivative is, it better have those properties. Negative here, 0 here, positive here. So now let's calculate the derivative. So let's get some x naught in R. Then f prime of x naught is equal to the limit as x approaches x naught of x squared minus x naught squared over x minus x naught. You good with that? Okay. Now, difference of two things to the same power can always be factored easily. So this is equal to the limit as x goes to x naught of x minus x naught, x plus x naught over x minus x naught. Good? Now, same logic, x is never actually equal to x naught, it's just really close. So this isn't 0, this isn't 0, we can cancel those out. And so you're left with the limit as x approaches x naught of x plus x naught. Right? And what's that equal to?
2x naught.
Just 2x naught. The limit as x approaches x naught of x is just x naught, and then the limit of x naught is just x naught. Add together, you get 2x naught. Okay, so now let's graph that function. What does f of x naught equal to 2x naught look like? Or in other words, another way that we can say it is f of x equal to 2x. Or another way that we can say it is y is equal to 2x. That's just a line whose intercept is 0 with a slope of 2. So it goes through 0 and it has a slope of positive 2. So it looks something like that. Which is what we expected our slope function to kind of look like. Negative over here, 0 at the origin, positive over here. Okay. Oh shoot. I think you guys have the definition of the derivative in your head now.
Yeah.
It's just the limit of the slope, the limit of rise over run. So, let's calculate another one. Let's calculate the derivative of f of x. What the weird? What the weird? Sorry. Oh. It's like my muscles are spasming every time I reach up like that. Try and write left-handed for a second. Let's go. Oh. That's killing me. Jeez.
Is it your thingy again?
No, that's just random. Babysitting will make it not so bad. Okay. Oh my goodness, I cannot reach up there. Alright, Jacob, come right. Right pretty. Alright, so f of x equals x to the n is what we're calculating the derivative of. Right?
Yeah.
So let's start calculating the derivative. Let's take the limit. Limit as x approaches x naught of.
Is it x n minus x naught n over x?
Perfect. So now we have a difference of two,
The difference is squares, right?
not squares, but two terms to the exact same power.
So this equals.
So yeah, what does that equal? How do you factor out an x minus x naught in that?
So it equals x minus x naught of x n minus 1
X naught to the 0, if you want to make the pattern explicit.
plus x n. Wait, x n minus 2, right?
Yeah, x to the n minus 2, x naught to the 1, minus 2, minus 2.
Oh, sorry.
There you go.
Dot, dot, dot.
Plus, what's the second to last term?
X n. Oh,
X to the 1,
1.
x naught to the n minus 2. X to the 0, x n to the n minus 1. Okay, so that's how you factor that difference when they have the same power. This is the formula from the preliminaries. I told you we're going to use it again and again. It's real easy to prove. If you don't remember how to prove it, you just multiply it back out and see that you get where you started.
Yeah, so don't you end up with...
Well, now you need your denominator. So now your x minus x naught and your x minus x naught, those cancel out. So now you're just taking the limit of that big polynomial to the right. And the limit of all the x's, you're just basically replacing all your x's with x naughts, right?
And so it's just x or x.
How many terms are there in that thing? There's n terms. And every one of those terms is going to be to what power?
N minus 1.
N minus 1. N minus 1 and 0 is n minus 1. N minus 2 and 1 is n minus 1. Remember, when you multiply terms together, you add the exponents. Right?
So it's x n minus 1.
So that's equal to, now just write it out. X naught to the n minus 1. We're taking the limit as x goes to x naught. And how many of those terms did we have?
N terms.
We had n of the terms, so you need your n coefficient.
In front of it.
Coefficient. There you go.
So not that, or keep...
No, both those are
Oh,
right.
right. I see
Yeah.
what you're saying.
Okay? So we did that, we did that, we did that. Okay. So now we're to the point where we're deriving what the derivative of a sum of two functions is, what the derivative of a product of two functions is, what the derivative of 1 over a function is, and then what the derivative of a quotient of functions is. Okay?
What's 1 over a function, isn't that? Oh, okay.
Yeah. So now let's do the sum. Let me see if I can. Okay, it stopped. Thanks. That was weird. Well, let go for a second. Okay, so let's start out with the limit of a sum. So we want to prove that, or the derivative of a sum. How exactly do they write it? Okay, here's how they write it. So if I have f and g are differentiable, then we want to prove that f plus g prime at x naught is equal to f prime of x naught plus g prime of x naught. You with me on what we're trying to prove?
Trying to prove what?
That the derivative of a sum of two functions is equal to the sum of the derivatives.
Okay.
So in other words, we calculated that, so if I had f of x is equal to x squared, and g of x is equal to x cubed, and then I make some new function, h of x is equal to f plus g, I want to know the derivative of this. Now I know the derivative of f of x, right? What's f prime of x equal to?
2x.
2x, using this formula right here. Whatever the power is minus 1, and write the power as a coefficient.
Oh, that's what we just did. I was like, wait, why do we do that?
Right? So what's the derivative, what's g prime of x?
3x squared.
That's 3x squared, you see that? Okay. So now, the question is, what's h prime of x equal to?
Is it 2x plus 3x squared?
Yeah, that's what we want to prove, is that it's 2x plus 3x squared. So, the derivative of the sum, remember h of x is the sum of these two things. Let me rewrite this one more way now. F plus g prime of x. The derivative of the sum is equal to the sum of the derivatives, because I could rewrite this as f prime of x plus g prime of x. See that? So that's what we're trying to prove. We're trying to prove that the derivative of the sum is equal to the sum of the derivatives. You can almost see how this is identical to our limit, right? So let's prove this. So I'm going to take this derivative and see if I get this out and I'm done. Okay? So what is this derivative? Let's calculate it. That is the limit as x approaches x naught of
F of x.
f plus g, f plus g of x
No. Sorry.
minus f plus g
Writing now.
of x naught over x minus x naught. Good so far?
Yep.
Okay. Now just writing out exactly what this is. F plus g of x is f of x plus g of x, right? So this is equal to f of x plus g of x minus, I'm going to distribute the minus to these as I go, minus f of x naught minus g of x naught.
Factor out. Oh, no, you can't factor that out.
Let me get some space over here. And this is still over x minus x naught, right? And then, oh shoot, forgot my limit. Equal to the limit as x approaches x naught, whatever, is equal to the limit as x approaches x naught. We're going to just reorder our terms. You can probably see exactly what we're doing anyways.
Yeah, it's gonna be.
To make it very clear, we're going to have f of x minus f of x naught plus g of x minus g of x naught all over x minus x naught. You get with that? Now the limit of a sum is the sum of the limits using our limit rules, right? So I can write this as two different limits now. So this is equal to the limit as x goes to x naught of f of x minus f of x naught over x minus x naught plus the limit as x approaches x naught of g of x
And those are just.
minus g of x
That's
naught
the
exactly,
definition of derivative.
over x minus x naught, which is by definition f prime of x naught minus or plus g prime of x naught. Any questions in any of the thinking that happened there?
No.
Okay. So now let's do the next one, which is going to be just as easy, right?
Yeah.
So now we're going to prove that
The difference.
let's get rid of all this.
We don't need to prove the difference, right?
No, difference and addition are the exact same thing. Yeah, we're going to do the product now. So we're going to prove that the derivative of f times g, the derivative of that function, you know what I'm saying so far? Is equal to what? The product of the derivatives, right? F prime of x naught times g prime of x naught. So we're going to prove that this is equal to this, just like good old Leibniz did. He said, obviously this is the case, but we'll take the time to prove it. All right, let's do it. So we have the limit as x approaches x naught of, I've got a product here. I'm going to go straight to writing it this way. Hopefully you're okay with it. F of x, g of x minus f of x naught, g of x naught over x minus x naught. You okay with me making that skip?
I'm pretty sure you can't do this.
Is equal to the limit as x approaches x naught. Now I'm going to add and subtract the same thing from the numerator. So we have f of x, g of x. I'm going to subtract f of x, g of x prime. And I'm going to add that again somewhere. Let's see, is that the way I want to do it? I'll have to reorder terms if I do that. Let's make this minus f of x naught, g of x. And then I'll add that term again. So, plus f of x naught, g of x. And then what was our last term? Minus f of x naught, g of x naught. All over x minus x naught. You notice what I did? I just added and subtracted this term. I added a 0, exactly.
Yeah.
So you go with the logic there?
Uh-huh.
Okay. So now, I'm going to, from these two terms, I'm going to factor out a g of x. And from these two terms, I'm going to factor out
F of x naught.
an f of x naught. So, we have, let's see, what was I factoring out here?
G of x.
G of x, thank you. We have g of x times f of x minus f of x naught over x minus x naught plus, and we're taking the limit of the whole thing, plus, let's see, what was I factoring out these? Factoring out f of x naught. F of x naught times g of x minus g of x naught over x minus x naught. You go with everything I did there?
Yeah.
I'm just reordering it to make stuff pop out very nicely. Because they still have a common denominator, so I could distribute that back in, treat it like one big denominator, and then you just have the numerator. So, y'all good with how this goes to this? Okay. Now, the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. You good?
Yeah.
I'm going to get crazy with limits on this one, but then you'll see how it all cleans up.
Just don't write x.
Limit as x approach. Yeah, should we just do limit now? Okay, it's implied that we're doing it x goes to x now. So we're doing the limit of g of x times the limit of f of x minus f of x naught over x minus x naught plus the limit of f of x naught times the limit of g of x minus g of x naught over x minus x naught. Okay, you good with all those limits? The limit of the sum is the sum of the limits, and the limit of the quotient is quotient, and the limit of product of limits. And now finally, what is the limit as f of x? What is this limit? Well, let's do it one at a
That's
time.
the derivative.
What's the limit as x approaches x naught of g of x? It's just g of x naught. Because we know g is continuous. I didn't say that at the beginning, but both these functions are differentiable, therefore they're both continuous. So the limit of that is that. You good with that?
Mm-hmm.
Okay. The limit of this is
F prime of x.
f prime of x. Not, right? Plus, what's the limit of f of x naught?
F of x naught.
Just f of x naught. Times, what's this?
G of x naught.
G prime of
Or
x.
G prime of x naught. Wait a second, that's not what we said. So, the derivative of a product is not the product of the derivatives. No, it's this thing.
It's
Okay.
So that was not true. It's this. Right? Is that what we have there?
Mm-hmm.
Okay. And then how we typically write it, this is the exact same thing, or at least how I'm used to saying it, is this. You see how that's the exact same thing?
yeah.
And then here's how we say it out loud. The derivative of a product is equal to the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Right.
Okay? So a little bit surprising here. The derivative of a product is not just the product of the derivatives.
Like it is with limits.
So that's a mistake that we know Leibniz had in his notes for a little bit before he corrected it. It's one of the reasons that it's never good for us to say the word obvious in math. Sometimes things that we think are obvious aren't obvious. Leibniz was a lot smarter than us, and he made the mistake of thinking that was the case for a second.
How do you know he's
Because he was smarter than me, and I know where I am relative to you.
Yeah.
Okay, so maybe let's do a quick example using this. You good with the proof on here?
Yeah.
By the way, I'm thinking for this test, I'm not sure if I'm going to do this yet or not, but I'm really tempted to make you guys do this proof. Exactly.
That would be so fun and easy. Wait, you should make us do all these proofs.
I'm thinking I might make you do this one, and I might make you do the quotient one, even though they're not going to be homework problems.
Do it. That's easy.
It's easy when you first see it and understand it. Then when you go to do it tonight, you might get stuck.
Okay, I'll get stuck on the plus.
Here's the big
Plus 0.
The big trick is plus 0. And notice that you did it so that they have one's using an x naught and one's using an x. It doesn't matter if you did f of x, g of x naught, you still would have gotten the same thing.
Right.
But you just add and subtract the same thing using both functions. One gets x, one gets x naught.
So what's the idea of adding a 0?
So that you can factor. The trick is we're trying to make this limit come up in there somehow and this limit come up in there somehow.
Okay.
Because these we know. So we're trying to make limits that we know pop up.
So why is this so important to put it on the test?
That you know what the product, how the derivative rule applies to products.
Okay.
It's one of the most basic types of rules you're going to use again and again and again.
All of these things are like right up. Like application problems, if we understand these, are going to be way easier.
Application problems, you're just using these rules over and over again. You're using the rule that if you have xn, the derivative of that is equal to n x to the n minus 1.
Yeah.
That's one that you use again and again. The sum one you don't really need to memorize because,
It's obvious.
or you don't learn it before because it's just how you expect it to be. And then f times g prime is equal to f prime g times g prime or plus g prime f. So that's two of the rules, and then we write out some more rules here. The other ones you're going to use all the time is the quotient rule and then the chain rule, and then that's kind of all your basic.
I never
Chain
understood
rule.
the chain rule. I'm going to be honest.
So I'm thinking I might just have you guys prove each of the rules that you use all the time as you continue on.
That would actually be so smart of you.
And we only have
That would help us so much.
We only have 4 sections.
Yeah.
In
Wow.
4?
Yeah.
Okay, well, you can put more problems on the test.
Yeah, I can do more problems on this, so maybe I will
Add these as
add each of these and then pick a problem from each section.
Okay, can I go real quick?
Sure. Okay, so the next one that we're going to prove is kind of like a lemma. It's not one that we really use directly all that much. It kind of helps us with other proofs, but it's not one that we directly use in application very often. And it's actually just a special case of the quotient rule. So let's write it out exactly. Okay. So now we want to do the derivative of 1 over g of x. The derivative of that is equal to the derivative at x naught is equal to negative g prime of x naught over g of x naught squared.
How would I look at 1 over g of x prime. How would that look?
How would that look?
Mm-hmm.
Well, an example might be, so if g of x is equal to x cubed, you know how to calculate g prime of x.
Mm-hmm.
G prime of x, you know, then is 3x squared, right?
Mm-hmm.
Using that top rule. Now the question is, should it be easy for you to figure out what 1 over g of x? What's the derivative of this? And then, based off of what we know we're going to end up getting, it's going to be negative 3x squared over x to the 6. Using this formula. So if I were to take the derivative, like if I were to do a longhand and actually calculate the derivative of 1 over x cubed minus 1 over x naught cubed all over x minus x naught, take its limit. If I were to do this in all the algebra, I'd eventually get this. And rather than having to do all this algebra, we're just going to prove it in general. Does it make sense what I'm saying?
Yeah.
Okay, so that's essentially what we're going to do. So what is this? What is the derivative of this? We're proving it's equal to this. We don't know it's equal to this. So what's the derivative of this? That is going to be the limit
As x approaches it.
of 1 over g of x. I'm going to stop writing as x goes to x now.
Plus. or
We know we're
minus-
not doing it as n goes to infinity.
Minus 1 over g.
1 over g of x naught all over x minus x naught.
Okay, so real quick, how is this proving the quotient rule?
This isn't a quotient.
It's a lemma.
This is a,
This is gonna, it's not really a lemma. I just have to kind of think about it as a lemma for helping us get to the quotient rule. Because obviously, if I know how to calculate the derivative of this, and I know how to calculate a product, I then know how to calculate the derivative of f of x
Right.
over g of x.
Right.
Because that's the same thing as 1 over g of x times f of x, use the product rule.
Okay.
A lot of texts I've seen don't bother proving this. They just prove the quotient rule, and then this is a special case of the quotient rule where the top's just 1. That makes sense? And we'll see it that way as well. We can see that. But let's calculate this derivative real quick. So this is equal to, well, what's the natural thing to try and do? Maybe get common denominator in the numerator, right?
Right.
So that's going to be g of x,
X
g
naught.
of x naught, minus g of x, all over g of x naught, all over x minus x naught. I'm doing this a stupid way so you guys can see everything. Now, it's equal to the limit of that is equal to, this is just g of x minus g x naught x is equal to the limit of g of x naught times x minus x naught.
No.
yeah,
Shouldn't x times x, shouldn't that be on the numerator?
This,
no,
what is 1/2 divided by 2?
1/4.
Okay.
Sure it's not 1.
Huh?
Sure it's not 1.
Positive. When you take a half and you divide it into 2, you end up with 2/4.
You end up with the whole thing.
Alright. Anyways, now what do we obviously see lurking in there?
The derivative of x, g of x.
Almost, we've got our signs backwards. We need g of x minus g of x naught. Right? So if I factor out a negative, then that's going to flip it. So we've got, and then I'm also going to split this into a product here, so see if you can follow all this, and I can explain it if it does make sense. So you good with that?
Mm-hmm.
Okay. And we have conditioned that g of x, I didn't specify, but obviously g of x can't be 0
Yeah.
anywhere while we're doing this. And g of x naught, obviously, too, can't be 0. Because you can't divide by 0.
Okay.
Right? It's the same condition that we always had anytime we took a limit of a quotient. Same thing. Anyways, so what is the limit of this? What's the limit of g of x?
X naught.
G of x naught. Limit of g of x naught is,
G of x naught.
so this whole limit is just 1 over g of x naught squared. You get that?
Mm-hmm.
Okay? Times, what is this limit?
Negative
Negative
G
G
prime.
Times negative g prime of x naught, right? Which is equal to exactly what we were after, negative g prime of x naught over g of x naught squared. Which is what we have here. Good? Any questions there? Any word steps there? That one's pretty straightforward. I mean, the only weird part would probably be, I don't know if there's anything weird. It's just like you're trying to simplify the whole time and it just comes out. Like I'm trying to think if you were doing this, where would you get stuck? Going from here to here, you should know to do
I would
that.
get
It's
stuck
the
on
next step
taking
that
the
would get
negative
stuck.
out.
So taking the negative out. Okay, yeah, that one kind of makes sense. So yeah, that is kind of a trick. Remember to factor out your negative. But outside of that, pretty straightforward.
Yeah.
But this won't be on the test.
What if you just make all of these
Maybe it
problems
will be.
extra credit?
I just like making money of making us torture.
Either that, or you'd have to prove the quotient rule directly without using this as an intermediate step.
Oh, this would be a part of that. Oh yeah, you're about to show.
Yeah, this is like we did a piece of the quotient rule proof.
Just like epsilon delta first. Like you almost have to do a whole proof and then do the whole proof. Just find your delta.
Did you hear
So
what's
now
that
we just
term?
going to find out that if we have 1 over g prime,
The whole proof.
that's equal to g prime over g squared.
A whole proof before you do the whole proof.
Negative G prime.
Negative g prime. Good job. Right? So now, let's do the quotient rule. So the quotient rule is, I'm trying to find the derivative of f over g at some point, and that's going to be equal to g of x naught f prime of x naught minus f of x naught g prime of x naught all over g of x naught squared. Okay? What are they called?
Wait, what the heck did you just do? Oh, you're trying to prove that's the case.
Yeah, we're trying to prove that's the case. What are they called? Phrases that you memorize to help you remember things. I can't think of it right now. Anyways, the way that I've heard this said is the derivative of the quotient is low d high, meaning the derivative of the high, low or bottom d high, minus high d low, square the bottom, and away we go. It's one of the things that I've heard to help memorize this.
Sounds like something Arrow would say.
But
Low be high minus high be
a
low.
lot of people just say the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. But low d high minus high d low, square the bottom, and away we go. Kind of like Socotoa, I guess.
Socotoa is the most useful thing.
Socotoa is.
Doing teaching's homework last night, and that's all I was using. That's right, Socotoa.
It just demonstrates a lack of intuition for the trig functions.
Well, it's,
So you're going back to something you memorized to help you calculate it. instead of-
when are we going to develop trig?
Intuition for trig functions?
When are we going to develop trig?
We're not developing trig in this class.
Or to
It's
build
calculus.
calculus.
This is calculus. You're supposed to do it in trig.
Yeah, when's that gonna happen?
Yeah, it doesn't happen anymore. You don't prove hardly anything in trig.
I'm asking you to teach us.
You want to do a trig class over the summer?
Yeah.
I don't have a good trig book.
Algebra.
I need to find a good trig book. I'm also really tempted by analytic geometry.
Isn't
I
that
want
what
to do
Oh.
A good piece of what we're doing
Doing
is
algebra.
analytic geometry sprinkled in.
Algebra 1 and Algebra 2.
Well, it wouldn't be like that. I would teach, if I do algebra, it would basically be college algebra. We just start from the beginning and prove, and we do algebra.
That would be a fun
Do
class.
geometry,
Huh?
geometry, any of them?
Algebra
Geometry's
probably
great.
better in
Huh?
college. Jumping into calculus in college, I'd rather algebra.
Jumping into calculus in college, you'd rather algebra. You're not going to start college in calculus.
You're not gonna start calculus in college.
You're not going to start with calculus in college. You're most likely going to start with college algebra or trig.
Okay, better read.
I've already taken calculus in college. Oh, no, I haven't.
Oh, yeah.
So I'm starting, I'm starting.
Okay, anyways, let's prove this. So, f over g prime of x naught is equal to f times 1 over g prime at x naught is equal to, you good with that?
Yeah.
I just split this up into a product.
Yeah.
Okay. Now we can use our product rule. What's the product of two functions? It's the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. So it's the first times the derivative of the second.
Wait, what's the derivative of one? Oh, right there.
Yeah, we have it, but for now I'll just write it this way and then we'll plug in. Maybe you write it like that. The first times the derivative of the second plus the second times the derivative of the first. You good with that?
That's not what that says.
Yeah, that's not what that says, so we need to fix that.
Oh, I wrote it backwards. Here's how I did it. The first times the derivative of the second plus the second times the derivative of the first. Oops.
Doesn't matter either way.
Sorry. Same thing though. You see how it's the same? Okay, sorry about confusion. Should have paid better attention to that. Anyways, so we got all this, now we just need to plug in what this derivative is. Right? So this is equal to f of x naught times, what is this derivative? It's over there.
G of x naught.
Negative g prime x naught over g squared of x naught plus, and I may combine these into one fraction. You good with that?
Yeah.
Okay. Now, I'm going to get the common denominator. So I'm going to multiply this from top and bottom by g of x naught. And I'm going to write this term first. Okay?
Okay.
So this is equal to, writing this term first, we have g of x naught, f prime of x naught. And it's all going to be over g squared of x naught, right? Or, sorry, g of x naught squared. Probably write it down. So there's my first term, right? Minus, and now write this term. And we're done. That's what we were trying to prove. Good?
Wait, how did you get a common denominator again?
I times this top and bottom by g of x naught. And I wrote that term first.
And you flip the minus sign around.
I pulled the minus sign out front.
That seemed right though.
What seems weird?
You pulled the minus sign out front. But how did it get there?
Okay, let me rewrite this again. And then go from that to that, like flip the order.
Oh, you flipped him around.
Yeah.
Okay, yeah. I'm just-
Good? Anything weird? All right.
Is that at the end of the section?
I feel like we skipped a verb.
We did, we skipped proving that a differentiable is continuous.
What number is that?
It's before this, it's right before some of the derivative of the sums.
Oh, well, we can't prove that right before class, did we?
Yeah, we did.
Okay, so here's what we skipped over. We know that a continuous function isn't necessarily differentiable, but is it true that a differentiable function is always continuous? In other words, if a function is differentiable at a point, is it true that it's continuous at a point?
So I proved that that's wrong.
No, we're going to prove that that's right now.
Or if continuity does not necessarily mean it's
Right, continuity does not imply differentiability, but differentiability does imply continuity. It is really boring. You can't feel as much over here. Blowing on that side from real bad. 73?
Yeah.
Maybe more like 71.
Dude, I swear these verses get so holy. They'll make the classroom so extreme, and so extreme, and so extreme, and so extreme.
71 extreme.
Yeah, it was super hot.
Last night I was turning on the cars for all our sisters, like, dude, go put it clear up to 90. All of them had a Fermat, like a thermometer or a panel in it.
In their car.
So you click up.
You're saying because they were scared, or they didn't want to go outside in the cold.
Yeah, they didn't want to go outside.
A lot of people have this weird idea
That you.
that cranking up the thermostat somehow gets it warmer faster.
Yeah.
And it doesn't. It still warms up at the same rate it warms up.
But not in
It's
like,
just now going to keep going.
not in a car where you twist it hot or cold.
Well,
Because
all their
if you
cars
twist
had
it,
that.
huh?
All their cars
Their
had
cars have thermostat.
Right, I know. I'm saying, but not.
I found it funny.
Well, it used to drive me crazy when I lived in the bunkhouse because we had like a little space heater, and people would crank up the thermostat all the way.
Yeah.
So the space heater keeps pumping away, even
Yeah,
if
my
it's 80 degrees
space
in the
heater.
room. It's like, what the heck? You guys just set it where you actually want it.
What I do is I crank it up, let it go past the point, and then I put it down. Because then it'll be really warm. Until it won't
Well, I
be
try to do
hit
the
the point.
I try to crank it up just enough so that the white noise will put me to sleep, and then it'll turn off during the night.
Well, driving with Rebecca is, she'll put it at like 80 normal so that she's warm. So I'll put it at like 59. And then I'll be perfect.
Becca, like your mother.
Yes.
Oh, you're saying Miss Rebecca? I was like, no, she sets that thermostat at -0 degrees
-0,
Celsius.
yep. -0.
Kelvins. Literally all destruction in there.
0 degrees Celsius is different from 0 degrees Fahrenheit.
0 degrees Celsius is ice, frozen.
Mine's 32 Fahrenheit. Or it's positive 32 Fahrenheit.
It's, yeah.
0 degrees
Celsius is 32.
I was reading-
What temperature does water freeze at?
32 degrees.
Fahrenheit. That's 0 degrees Celsius. Celsius scale is defined so that 0 is a temperature that water freezes at. I think it's at sea level because your altitude changes boiling points and freezing points. And 100 degrees Celsius is defined as a point where water boils. So 0 is where it freezes, 100 is where it boils, and then you have an even tick mark in between.
Okay, 0 degrees Kelvin,
equals
so.
to 0.
0 degree Kelvin.
32 degrees Fahrenheit, yeah, I don't remember the exact story for how Fahrenheit came about, but basically he made 0 degrees Fahrenheit the coldest temperature he could produce in his lab. So that was the coldest temperature he could produce in his lab to, I guess, what's it called?
We're so stupid.
When you set
That
an
seems
instrument.
inaccurate. Really inaccurate.
Yeah.
To calibrate the instruments, there we go. Inaccurate?
Yeah.
It's not inaccurate, it's just arbitrary. You gotta pick something to be 0.
Oh.
And I can't remember how he picked his other number.
Boiling point, 212.
Well, if I pick one temperature to be 0, so this temperature we'll call 0, and I pick this temperature to be 1, now I have a full scale.
Right.
So once you pick two numbers, then you have a scale. So we picked 100 to be the boiling point of water, 0 to be the freezing point of water. Okay, you just created the Celsius scale. If I pick
34.
32 to be the temperature where water freezes, and then I don't know what water boils at, 212?
Yeah.
212 to be where water boils. Okay, I just created Fahrenheit. Now this isn't how he created Fahrenheit, but you can do it and you get the same thing.
The Kelvin scale and the Celsius scale are the same thing, aside from shifted 272. So 0 degrees Kelvin is
0.15,
is
right?
absolute 0. What? From Celsius to Fahrenheit, it's times 1.8.
Celsius, Fahrenheit, no, you have to add a constant.
Yeah,
I remember how to do the
plus
conversion.
32.
Yeah, it would have to be 32 because 0 corresponds to 32. And then that's probably still just a rough approximation that doesn't hold for high numbers.
Yeah, when does it get more than 1,000 degrees?
Anyways, let's continue with housing mill rings. And suppose if I is a neighborhood of X naught and
You just really reminded me of something.
F from I to R is differentiable at X naught, then F is continuous at X naught. Okay, so let's remember our definition of continuous. Now we have a few definitions of continuous at this point that we could use, whichever one we want. We know our limit of a sequence definition. We know our epsilon delta definition. The most convenient definition to use for this group is a function is continuous at a point x naught if the limit as x approaches x naught of f of x is equal
Zero.
to f of x naught. If this is true, then the function is continuous at x naught.
I didn't know that was one of the things.
We almost proved it right after we defined what we mean by this. Limit as x approaches x naught. And it's very similar to the limit of a sequence. We just put a restriction that the sequence can't ever use x naught. Anyways, so that's the most useful definition, continuity, to use in this. So I know that a function is differentiable at a point, prove it's continuous at a point. Okay?
So what does it mean if it's to be differentiable?
Yeah, since it's differentiable,
Donnie, this is low battery. It's not
did I not plug this in? Good thing you caught that.
How does one go?
Hopefully that doesn't.
Last time it did.
Still going. Okay. So, we know it's differentiable, so observe that the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is some number f prime of x naught. It exists. Right? Well, what does that give us? I'm not going to use a lot of words, I'm just going to keep doing implies arrows and rewrite equations. Well, that gives us that the limit as x approaches x naught of f of x minus f of x naught is equal to f prime of x naught times the limit as x approaches x naught of x minus x naught. Good with that? That gives us, taking our limits, well, I'm going to split this one up.
Wait,
So
no. I don't understand what you did.
multiply both sides by the limit as x approaches x naught.
Oh. Yes.
Okay, so now we're here going to here. I'm going to take the limit for this term, not for this term. So I have the limit as x approaches x naught of f of x. What's the limit of this portion? Just f of x naught. So minus f of x naught. You good with this to this? Is equal to, what's the limit as x approaches x naught of x?
0.
It's not.
X naught minus x naught is 0, so the limit of this whole thing is 0. So f prime of x naught times a big fat 0. Maybe we'll just write 0 over here altogether. And then that gives us, moving this to the other side, we get that the limit as x approaches x naught of f of x is equal to f of x naught, which is what we were after, right? That shows it's continuous.
That is an easy way to show it's continuous.
That's an easy way to show it's continuous? I don't know what that means, but it's the most convenient definition of continuous to use in this context because we're taking the same limit there that we're taking there. Otherwise, we'd like to have to convert to sequences somehow. Anyways, so that's our proof that if it's differentiable, it's continuous. And then obviously the opposite doesn't hold. Let's see, another. For an integer n, define set that to be r if n is greater than or equal to 0. For an integer instead of an natural number. Okay, so the next thing we're doing basically is how do we calculate the derivative when we have x to a negative power?
Where are you? Proposition. Okay.
Where x not, or where x is smaller than. Sorry, where x.
I'm looking at
is smaller
proposition
than-
4.7. So 4.7 is saying
For an integer n, define set Is that a Q or a
No. So it's saying if f of x is equal to x to the n, where n's any integer now, not just a natural number. Remember when we did this, we said it was a natural number. If we're going to do an integer, let's pick something different. Let's do a. F of x is equal to x to the a, then f prime of x is equal to a times x to the a minus 1.
So we're just doing the same thing for integers now.
So now we're doing it for integers instead of just natural numbers. Okay? And it specifies if a is a number that's less than 0, so if it's a negative integer, or if it's, negative integer, then x can't be 0. Why can't x be 0 if a is negative? Remember we defined x to the negative 2 is equal to 1 over x squared. So x, when you have a negative exponent, it's 1 over x to the positive version, which we can't have 0 down here. So they have a conversation about, we're taking f of x is equal to this, where the domain of this is all real numbers if a is not negative, and it doesn't include x if a is negative. You with me? But we're kind of going to ignore the technicalities with the domain, because you understand that. So we have two cases. A is either a natural number or it's not.
If it's a natural number, it holds. If it's 0, it's 1. Or it's just x. If it's negative, then we have to figure that out.
Well, for it being 0, we just get a constant.
Right.
And what's the derivative of a constant?
The constant.
Maybe we should have a quick side proof. I don't know if we explicitly did this yet or not. But if f of x is equal to a constant a, f prime of x is equal to 0.
I remember that.
Oh, right.
Which should be pretty obvious. The limit as x approaches x naught of a minus a over x minus x naught is 0. Good?
Yeah.
So the derivative 0 when we have x to the 0. Good? So we know 1. If a is greater than or equal to 0, then we already did. We've already done it here for when it's greater than 0, and we already know it's 0 when a is equal to 0. So we don't need to worry about those two cases. All we really care about is the case where a is less than 0. Good? If a is less than 0, then there exists some natural number such that negative n is equal to a. That's what it means to be a negative integer. Right?
Mm-hmm.
So f of x we can now view as equal to x to the negative n. Or to the a,
That
right?
makes sense, yeah.
Which we also know is equal to 1 over x to the n.
Mm-hmm.
Okay? Then f prime of x is going to be equal to, how do we take the derivative of this? Try here. Right?
Yeah.
So the derivative of 1 over a function is equal to
Function.
the derivative of it, negative the derivative of it over its squared. So what's the derivative of x of n?
And of x minus 1.
Right?
Mm-hmm.
That's the derivative of x of n over x of n squared. Good with that?
Yeah.
Convert your n's back to a's.
Yeah, let's do some conversions. Negative n is the same thing as a. And then we have x to the n minus 1 minus 2n, bringing those two n's up here. You good with that? Okay. Which is equal to a to the n minus 2n is just negative n. So we have negative n minus 1. Oops, I missed my x. X to the negative n minus 1. You good with that?
Where did your x on the bottom go?
Fucked up.
Let's do this slower then. So this is equal to negative n times x to the n minus 1 times 1 over x to the 2n. You good with that?
Mm-hmm.
Which is equal to negative n times x to the n minus 1 times x to the negative 2n. You good with that? And now when you multiply terms, you add exponents. So now I'm going to make my substitution for negative n is really the same thing as a. And now I add the exponents together. I have n minus 1 minus 2n. N minus 2n is negative n. And then we have our minus 1. You good?
Mm-hmm.
And then negative n is obviously the same thing as a. So we proved it. F prime of x is equal to a times x to the n minus 1. So in other words, now if I said, if f of x is equal to x to the negative 4, what's the derivative?
Negative 4x.
F prime of x is equal to negative 4 x to the negative 5.
It's weird. Okay.
That is kind of weird.
So now you don't need to remember the specific case. You can remember that this holds for any integer. So now n can be an integer. It doesn't necessarily have to be a natural number.
Okay.
Good?
Mm-hmm.
Okay. And
There's a lemon.
corollary. For polynomial p and q, defining the set of, select q of x is never equal to 0, then the quotient is differentiable. Oh, the quotient of two polynomials is always differentiable, let's see.
Makes sense. Because the quotient of two polynomials is just always going to be a polynomial. Right?
No, the quotient of two polynomials is not a polynomial. That's what we call rational. A polynomial can't have negative exponents in it. This is not a polynomial.
Yeah, I remember it.
Okay. If f and g are polynomials and g not equal to 0, comma, then f over g is differentiable. Understand what I'm saying there?
So when
You have two polynomials, f and g, the denominator is never 0. Then you can take the quotient of those two polynomials. Or you can take the derivative of those two polynomials.
Isn't that a polynomial up there? That very first one.
This is a particular polynomial when n is a natural number. Start with this. If that's a negative number, it's not a polynomial anymore. So let x not be any real number, and let g and f be polynomials. 0 in the denominator. Good? So now let's take the derivative. So then, the limit as x approaches x naught of f of x let's write this. So then g over, now we can do f over g. Then f over g prime at x naught is equal to, just using the quotient rule directly, right? G of f prime of x naught plus or minus g prime of x naught over g of x naught squared. Okay, so the derivative of the quotient of these two polynomials is going to be this. Since we know that g is never 0, this is okay, we're not dividing by 0. So now the only question that remains is, are we able to take the limit of f of x naught, and are we able to take the limit of just a polynomial? If we're able to take the limit of just a polynomial, then we can take the limit of their quotient. You see, the only question that remains in this whole thing is, were we able to find this limit, and were we able to find this limit?
Because that's polynomial.
I probably should have started by arguing that those limits exist. We know that a polynomial has a value, so this term's fine. But do we know that a polynomial always has a derivative at every point? So that's the one thing I probably should have said before this. If I can show that a polynomial is differentiable, then the quotient of the polynomials is differentiable where this isn't 0, right? So the last question remains, is a polynomial differentiable? And what is a polynomial? Remember, a polynomial is of the form a naught x to the 0 plus a1 x to the 1 plus a2 x to the 2 plus dot 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 plus an x to the n. Right? So then the derivative of the polynomial is obviously just f prime of x is just going to be a naught plus a1, oh sorry, this one's 0. 0 plus a1 plus 2a2 x plus dot 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 plus n x to the n minus 1. Nothing wrong with that. So the derivative of a polynomial is always differentiable. So the quotient of polynomials is always differentiable. So a rational function is always differentiable. Good?
Yeah.
And then you can read their explanation for it. They give a really short explanation, so probably not the best.
Yours probably wasn't the best.
But their explanation probably wasn't the best.
It's more simple.
Mine's probably not better than theirs, I don't know. You can read theirs, look at mine, whatever makes sense to you is what makes sense to you. Okay, so that finishes 4.1. Moving on to 4.2, we get into inverses. Inverse functions. The derivative of inverse functions. Huh?
I do that.
Sorry, what?
I said do.
Do? Why is that do?
Because inverses are something.
Now, to help give the intuition for what exactly is going to come out of an inverse function, let's think about what an inverse does. An inverse function just switches the x's and the y's, right? So if I have, so here's my system. If I have, this is my y, this is my x, and I have some curve here. There's my curve, here's x naught. The derivative at x naught is then going to be the slope of this line. Right? Now, when I swap my y's and my x's, how can I okay, so the slope of this is going to be my change in y over my change in x, where this function right here is f of x. You give it an x and it spits out y, and our slope is going to be y over x. Well, our inverse function, we can think about, you plug in y's and it spits out x's. Same thing, I guess. You plug in y's and it spits out x's. So now you think about it rotated like this. We're plugging in y's and we're spitting out x's. So now the slope of this thing is going to be x over y instead of y over x. Okay? So, in other words, if I know that f of x is equal to, well, I think what I said there was pretty good. If I know that f prime at x naught is equal to n, then f inverse, I'm not sure how to do the prime with it. How did they write it? Oh, did they just avoid ever having to use that notation?
Just put in parentheses prime.
So, yeah, f prime at y naught, where y naught is equal to f of x naught.
Prime at y naught.
The derivative of f inverse at y naught is equal to 1 over n.
Yeah.
Make sense?
Yeah.
So that's the big intuition for the results that we're going to see coming out of this. Actually, maybe we should do a break right now and then continue, right? We're basically halfway through. So let's do break, and when we come back, we'll do inverse functions. But there's the intuition for it, and then we'll start actually proving this. And maybe do some examples, see it in action.
Jot down those the great Western works of the world. The great works of Western history, whatever.
The great works of Western civilization.
You expect me to follow that? The text is like Numbers 6, if you were to put it to word, and it's like takes up the whole page. Like I couldn't read a sentence without losing my spot on the page.
Oh yeah, they're very dense books. They have a lot of words per page.
Yeah.
And the pages are really thin.
Yeah. Whoever did that. They have different authors, I noticed that.
This is not an author sitting down writing these things.
Oh my gosh.
This is, I know that Mortimer J. Adler is one of the people heading it up, but it's him and some group of people collecting the great works and putting them together. So they didn't write anything.
So like going from book to book, you're gonna get completely different language, like completely different voices.
Yeah, they're going to have completely different authors. You're going to read Plato, you're going to read Aristotle, you're going to read Euclid, you're going to read
His direct
Archimedes.
words, not someone
His
reading
direct
it.
words. You're not reading someone talking about him, you're reading their direct works. Now, obviously, someone translated it.
Right, obviously.
And I don't know if there was any coordinated effort to try and get like the same translator for as many works as they could.
So, did you say that they have like an advisory reading schedule?
Yeah, so in the first book they have a 10-year reading plan, which is meant to give you the highlight of all the books. So you have a sense of all the books, what they go over, and put it through in a nice order, kind of being consistent with topics rather than just reading a book start to finish and next book start to finish. Trying to have a coherent way to tie it all together. So I would never do the 10-year reading plan.
You would never do it?
I wouldn't do the 10-year reading plan. I
I would
always,
just start with Aristotle though? Or Plato, I mean.
for philosophy, I'd start with Plato. I doubt I'll ever go through all those works because a lot of them I just don't care about.
Because a lot of them are a lot of political arguments.
Well, they're color coded. So books that have a yellow bar on them, I'm not sure exactly what it is, but it's like yellows, literature, blues, philosophy, greens, science, orange is history, whatever. So they have all the different areas that it's covering. I mean, like, I would never read Shakespeare's, for example.
Right.
I would never read the Iliad and the Odyssey. I don't care about those. So there's a lot that I just wouldn't read.
I was actually going through those books, and it's funny because in my sophomore year, I was writing a research paper on the fall of Rome, and I used one of those books from Gibbons. Who wrote it? I don't even know his first name. But I used direct quotes from his book, and I didn't realize
Virgil?
that. Gibbons, that was the author.
Oh, Gibbons?
Yeah.
I'm not familiar with Gibbons.
It was the fall of the Roman Empire.
And he's a historian at the time?
I just used his, he kind of had like a side thought that was like 3 pages of how the adoption of Christianity had an effect on the fall.
Was he a general?
I don't know.
I can't remember the names very well of the historians I've come across. I have to look it up to see if he was one, but the name just doesn't ring a bell.
So the collection is complete though?
No, they got us.
Darwin is,
I think Darwin's the last book that they got to. The last author. Freud might be in it.
and Euclidean geometry is where mathematics starts? Or is that where science starts?
So, first off, those aren't very well defined terms. I mean, when the first caveman counted, did he do math?
I mean, math that.
And when the first person realized that when you drop a rock it falls, did he do science? So, when did math start, when did science start? That's a hard thing to do. But what Euclid did is, as far as I know, it's our first attempt at a consistent system. So he doesn't quite get it right. The one leap that he never made is that you have to start with undefined terms. And your axioms give meaning to undefined terms. You can't define everything. He tried to define everything, it doesn't work. Because some of his definitions just like beg the question, well, what do you mean? So for example, he said, a point is that which has no part. Which gives you some intuition for what a point is, but then that doesn't really tell you what a point is. What do you mean it has no part? Oh, well, it has no width, it has no breadth, it has no height. Well, it turns out as you're defining what those things are, you're going to have to use points.
Oh, yeah.
So there's going to come some point, if you keep trying to define everything, you're going to end up using circular logic somehow, circular reasoning. So the one big leap that he didn't make, that we use today in consistent systems, is you start with undefined terms. Outside that, you started with definitions, which is part of the consistent system, axioms, and theorems. The only thing he didn't have in there was undefined terms. Don't try and define one. And then he just made a huge leap. So he did a really, really dang good job, and we didn't really improve on his math until over 2,000 years later. I mean, it's insane how long it took us to think, no, here's a slightly better way to do it. And then the other thing that we are more precise on is what our axioms are exactly. We have more precise axioms than what he used.
So if I was to go over his geometry, then it would have holes, or would they have put in those holes?
It's not.
Is it not like a textbook?
It's not holes. It's like we do it all the time in this class. Similar things to what he does. It's like I say, you see how we do this, and we skip that detail. He skipped details.
Okay. Oh, so he still built it.
He still built his system, and he proved it. He had his postulates, and he proves everything from those postulates. It's just there's places where we say, by modern standards, you're playing fast and loose, and you need to be more rigorous. So we have more rigorous ways of developing the same thing. And we're not proving different things than what he proved. We're proving exactly what he proved, We're just doing it more rigorously. Which is what I did in that geometry class. We used, what's his name? I should know his name. I'm terrible with names. I'm not going to come up with his name. Wow. Hilbert. There we go. We used Hilbert's axioms. And Hilbert, we're talking about someone who was, his career was like 1900.
Oh, really?
Yeah. So he's the one that added to the system and made it more rigorous. And so Euclid's Elements, his textbooks for learning math, those were standard textbooks for learning math, clear up until like 1900.
Right.
Around the world. If you were to go to university and take geometry, you would go through Euclid's Elements. That's exactly what you would do. That was how you learned math. And so he proves math. He took all the knowledge of math at the time that there was, and he organized it into the system. He said, he started out with 5 postulates and 5 axioms, but another thing he didn't realize is there's not really a difference between a postulate and an axiom. He didn't call them axioms, he called them common notions, and then postulates, which were more geometric in nature. But from his 5 postulates, all the math at the time can be derived. So there were all these theorems already. People knew that if you had this, then you could get this. But he took it and made so that every theorem built on itself and came all the way back to these postulates. He said this theorem uses these theorems, these theorems use these theorems, these theorems use these theorems, all the way back to his postulates. So it all comes from this. So if these 5 postulates are true, then all of geometry, all our math is true.
Have we added onto that list?
Oh yeah, we proved tons of. I don't know if you by list.
I'm talking about the 10 assumptions.
We made them more explicit.
But there's still 10, or is there more?
The number of axioms that Hilbert has, it's more. It's something like 20 or something. I don't remember the exact number.
When we change it big time?
Well, we just got more precise because it's still. I mean, the geometry we use today and Euclidean geometry, they were capturing the same ideas. They were describing the same system of math. But we have systems of math that aren't geometry. But every system of math is just like the geometric system of math. That's why geometry is such a great field for students to go through. Because geometry is actually pretty easy. It's pretty intuitive. That's how I should say it. It's pretty intuitive. You can see the axioms. It's easy for you to understand what the axioms mean and see how the axioms lead to the results. See, in this class we started with our axioms and we got our results from our axioms, but it was much more abstract than Euclid's postulates. Euclid's postulates, for example, are the first one is 2 points define a line segment. If you have 2 points, that defines a line segment. This is a nice one is a line segment can be extended indefinitely. This next one is if you have a point and a line segment, that defines a circle. You take the line segment, stick it at the point, draw it out, okay, there's a circle. Now, he thought about a circle the way we think about a disc, but that's just a difference in vocabulary. His next postulate was all right angles are congruent. That is congruent to that. And then his last postulate, this isn't the verbiage he used, but it's logically equivalent, is if you have a line and a point not on a line, there's only one line I can draw through that point such that these 2 lines don't intersect.
And that's a parallel line.
And we call that parallel line. So those were his 5 geometric postulates, and from those postulates you can get.
Yeah, that's all very intuitive.
Yeah, they're very visual, and you can see them. That's why it's such a great. It's a great system of math for students to learn because it's your chance to learn a consistent system from the beginning. I can tell you every assumption that we're going to make, and I can show you how everything that we use from there on out comes from just these assumptions. And that's how all math is.
Did we build calculus off that?
Yeah, we did the same thing with calculus. We started out with our postulates. You know, we didn't.
Way back.
Yeah, we didn't go way back. We kind of said the real numbers we're going to define to be the set that satisfies these properties. So it's a set that satisfies these properties. added a few more axioms as we went. And yeah, but that's exactly what we did this class. We started with all our axioms, and if our axioms are true,
So what does this eventually build? Like things that I've seen.
geometry,
Yeah.
Pythagorean theorem.
What else? Because that was like super.
I mean, how do you calculate the area of a rectangle? The fact that if you have a triangle and this side's congruent to this side and this angle is congruent to this angle, all your ideas about
Side, angle, side, angle.
ratios could be re-demonstrated using triangles. When finding out ratios are congruent, I mean, there's tons of geometric theorems.
See, isn't that building trick?
Trig is an extension of geometry.
Oh, really?
Yeah, trig, you're just limiting yourself to
Triangles.
triangles. Or analog geometry is an extension of geometry. So what analog geometry does to geometry is it puts geometry and it combines it with the coordinate system. So now I have geometry, I combine that with the coordinate system, so now I can start talking about points as coordinates. It combines numbers with geometry. See, geometry prior to analog geometry doesn't really have numbers. I mean, you don't really see it that way because in the school system that we have now, anytime we give you a geometry problem, we also throw numbers all over it. And so you never get the sense of just doing geometry. You're always like calculating some algebra problem with geometry helping you along the way. But when you go through Euclid's elements, I mean, the vast majority of it, numbers aren't used. They are, but behind the scenes. So he would say something like, the area of this is equal to the area of this. And of course, we think about area as a number that represents something, but that's not necessarily how they're thinking about it. So they don't use numbers directly. And it wasn't until we got to analytic geometry, the idea of representing points as coordinates as well, that you get that combination. And that's what we call analytic geometry, which makes a lot of geometry way easier. Because there's some proofs that are real easy to do with analytic geometry that are kind of a pain in the butt with just geometry.
How did we start to find calculus?
We started by
How did we start to find
Like,
calculus?
okay, like, there's always like, I don't know, it seems like there's always a story. Like, a question was posed and they started to figure out, like, the apple falls on Newton's head, and he's just like, oh, let's see what gravity is. Why did this happen? Like,
Gravity was examined prior to Newton's time. People just thought it was an electric force.
like,
I should
see
say
what I mean?
there were people who thought it was.
Like, what question in the world posed?
Well,
Just
the
shot it off.
beginning of calculus goes back to Archimedes trying to calculate areas.
On a graph.
Well, could be on the graph, but you could graph it. But
When was Archimedes?
yeah, he didn't have analytic geometry, which was his big holdup. By the time Newton came along, Newton had already come up with analytic geometry, so Newton had analytic geometry.
Isn't Newton
And you could extend it, and then Leibniz as well.
the main head in calculus?
Who?
Isaac Newton.
So both Newton and Leibniz simultaneously derived calculus, but the earliest integrals, I don't know at the earliest integrals, but Archimedes did figure out how to calculate specific integrals.
Archimedean property.
Yeah, the Archimedean property.
How old was he? Before Newton or before Euclid?
No, he's after Euclid. He's way
I thought
after.
he said analytic geometry was Euclid.
No,
That was like,
Euclid was Euclidean geometry. So, Euclid and Euclidean geometry.
was Euclid a Greece? Where was he?
I think he was in Alexandria, but we call him.
But like BC.
Oh yeah, he's BC. He's not that much after because he has to be after Alexander the Great because he was from Alexandria, a city that Alexander named after himself. So you have Euclid. Let's get timeline. Here's 0. Here's Euclid. I'm not sure where exactly, but somewhere in here. Here's 500 BC. 500 AD. Archimedes is going to be somewhere over here because Archimedes was alive when Rome annexed Macedonia.
Annex. Does that mean cut it up?
No, when a state annexes a piece of land and they bring it into their state, make it part of them.
But the Roman Empire fell in like 360.
It fell around 500.
It did?
It started roughly 500 BC, ended roughly 500 AD. I don't remember what exactly the years are, but really close quotes. When I say the Roman Empire started, that's a bad verbiage. The beginning of the Republic is like 519 BC or something like that. And then the sack of Rome is somewhere around 500 AD. I don't know the sack of Rome. So if you use that for the beginning and
And
beginning.
then it separated into like Western Rome.
Yeah, it's divided into the western half and the eastern half, but was still referred to Rome. And then when Rome got sacked, the western half of Rome fell. The eastern half stayed intact as the Byzantine Empire, which continued for another 1,000 years. So that's where they are. And then Descartes, doing analytic geometry, is over here around 1500, I think. And then you have Newton after him, obviously.
Was Newton before Joseph Smith?
Yeah. Newton, I want to say, is early 1700s. I'm not positive. Might even be earlier than that. I'd have to think about it. Anyways, so that's roughly the timeline. So
Did Archimedes call calculus?
no, and calculus is just a word basically capturing calculate. I mean, the fact that we call it calculus is very much associated with what it is.
Okay.
And what
It's so weird that there's massive holes. It just doesn't make sense in my head. Like if someone was saying it, if someone had it right there, or was talking their language, why did it take so long to develop Archimedes or advanced geometry, whatever you call it? It's weird how there's massive gaps. Is all I'm saying. If someone started to develop an idea, you'd feel like it just continued to get pushed.
if someone starts to develop an idea, you feel like it would just continue to get pushed.
Yeah.
Well, so part of that could easily be a consequence of the modern world we live in. We have so many people alive now, constantly working to progress the body of knowledge. And naturally, you're going to have a lot of geniuses doing that simultaneously. If you're talking about in a time where
You know, if you had a good
the majority of the population that lived there wasn't formally educated, and then people are going to have their individual interests, and you even have limitations by the state. I mean, we live in a time now where it's not even close to possible for you to keep up with the body of knowledge. Even if you knew everything that was known right now and spent the rest of your life trying to keep up with a particular field, you couldn't do it. There's no way.
A particular field.
A particular field
You're kidding me. Mathematics is still progressing fast.
is still progressing. I mean, how many mathematicians are going to get their PhD this year?
Well, kind of
Well, you know, throw out a wild guess.
3,000.
Okay, we'll say 3,000. Have you seen a dissertation before?
Well, maybe.
It's a book.
Yeah.
Let's say that you're absurd and you're reading a dissertation a day. That's insane.
Is it just a bunch of proofs or what?
It's their addition to the field of knowledge. A dissertation is adding to the field of knowledge.
people are writing books,
You have to.
adding to the field of knowledge.
Right. That's what you do when you get a PhD. You write a dissertation, which is you need to go and do something that hasn't been done yet.
Brother Polly did that.
Yeah, he did that.
Levi
He
did
wrote
that.
a program for something with school systems. I can't remember exactly what it is, but yeah. And he had his dissertation explaining what the program would do and how it would do that.
And Levi did that with sound.
So this is
I
how.
know Levi wasn't mathematics, but
Well, the Levi must have done a dissertation, but this isn't what doctors do in general. It's what PhDs do. I think all PhDs do. There could be exceptions to the rule. Because there are some doctorate degrees that are a degree of practice rather than knowledge.
like medical.
Yeah, like an MD. You're not doing a dissertation if you're an MD. You're getting sole practice. There's similar ideas for getting a master. So you can get a master, for example, and I know in mathematics I can get a master's that is, you do this much schooling and you get a master's, and you basically have a big final test that you have to pass, and you have a master's, or you can do what's called a thesis route, where you have to do a thesis, which is like a mini dissertation. So there's two routes to go, same thing with doctors. But yeah, so more than 3,000, or if we're saying 3,000 people got dissertations this year, and we're saying that you can get through one dissertation per day, you're already being outpaced. You can only get through 365 of those per year.
Some of that's not going to be new.
It's all going to be different somehow. It can't just be, I mean, okay, maybe some of these are repeating. That's possible. Someone beat you to the punch.
But it's like, we're actually discovering new things.
Yeah, all the time.
Why do I not hear about it?
Because
Do I see it
not
now?
everything is just a big, massive deal. A lot of it is just slowly turning away, getting further, getting further, getting further, getting further, getting further.
Will we soon hit a big massive deal? Like oh my word, all of a sudden we can make buildings levitate.
Well, that's not a mathematical feat, but
Well, that's consequence of math. Consequence of calculus is
so one of the last huge big breakthroughs was the proof of Fermat's last theorem, which someone did. Do you know Fermat's last theorem?
No.
Okay. A to the n plus b to the n equals c to the n. If n is 1, can you find numbers a, b, and c that make this true?
Yeah.
Yeah. 1 to the 1 plus 3 to the 1 equals 4 to the 1. Okay, I found an a, b, and c that make this true. What about if n's 2?
Yeah.
Can you
Yeah.
find numbers a, b, and c that make this
3
true?
squared
Sure.
plus 4 squared is 5 squared.
Fermat's last theorem says, for n greater than or equal to 3, there are no solutions. You can never find an a, b, and c where that's true.
What?
You cannot find 3 numbers. So that the first number cubed plus the second number cubed
Real
equals the
numbers,
third number cubed.
real numbers,
Well,
they have
like
to be
Real numbers, yep.
weird. Okay, see, like that's not going to develop in me. It just says. Is my perception of math off? But I thought the only reason we even jab at mathematics was to build a better world.
First off, you're already imposing yourself on it. When you are saying a better world, what does that mean? A more convenient world?
Yeah,
Is that necessarily better?
yeah.
No, it's not necessarily better. Have I told you the anecdote with Euclid and his student? There's Euclid and he's with his student and they're doing a proof. And the student finally pipes up and says, how is this ever going to profit me in life? Euclid gives him some money. He says, there, you profited. Can we get back to what's important?
It's like discovering the mysteries. What if you could sum it up? Why? Why push to figure out the unknown? If it,
I mean, you can think about, to help appeal to your intuition, you could do like a thought experiment. Let's say, Jacob, that I am going to give you all the conveniences of life that you could possibly imagine for the rest of existence. On condition, from here on out, you can never learn.
Okay, why do I feel like I need to learn? Because that's how I felt.
Well, I mean, if you want, you're asking for a big argument in a second, but
I'm just wondering.
all men, by nature, desire to know.
Okay, but like,
By Aristotelian thought, knowledge is a need.
at some point, that you could grow your knowledge on weirder things. Like, this seems like something really weird to grow your knowledge on.
What better to grow on? This is the most objectively true thing you can find.
True?
If we know that anything is true, we know that Fermat's last theorem is true. If we know that anything is true, we know that 1 plus 1 is equal to 2 is a logical implication of our axioms that we have in our definitions of numbers. If we know anything, we know that. There's nothing that you come into contact with that you are more sure of than this.
So the only reason we develop or build math is to make us feel good about knowing a lot of stuff.
The reason that we develop math is to be happier people.
Seriously. So knowing more about some random something you did a long time ago, or everyone did, makes us happier.
Well, think about it if you want to have a practical end. Okay, I want practical knowledge. Why? Let's say I go and I take all this time to learn how a car works. Why?
So I make money.
Why?
So I can have food on the table.
Okay, so I can keep living. Why? What about it inherently in life makes it worth living still?
People.
Why?
Because people and friendships and kids and family bring happiness.
It does bring happiness. Those are parts of happiness. So does knowledge.
See, it does not make sense to me why knowledge is part of that picture. Like, I understand, like, I literally feel better. I would feel better if I lived a life where all my needs were met, like you said, but I couldn't learn. Like, I would feel worse in that situation. I feel like I'd feel worse.
That's a terrible situation. Having everything convenient is not something that you inherently enjoy. Think about a video game that you want to play. And I just make everything real easy for you. And now it's real convenient. What's the fun in that? There's no challenge. There's no improvement. There's no progression. Your existence void of progression is something that you would bail out on, I think.
Okay, but like, knowledge elsewhere is also knowledge.
To what extent?
Like
Give me a piece of knowledge that you have that doesn't presuppose mathematical knowledge in some way.
George Washington led the army.
How many years ago?
200.
You doing some math calculating going on there?
That's so stupid.
You're presupposing 1 plus 1 equals 2 in what you're saying.
I'm in this room.
There is a fundamental assumption. Who's the not mathematician, the philosopher that goes back to it? I think, therefore I am. So you do have what are called first principles, if we're talking philosophically, that you build your thinking systems on. I'm not sure the right verbiage to use for it. And so you have to use those first principles to develop logic, to develop math. So math isn't the first thing you suppose. The first thing you suppose is that you. You suppose you.
For some reason, I feel depressed thinking that what makes me happy is obtaining knowledge. That doesn't seem like a happy life.
It's progressing.
It is.
Well, so in short, here's what Aristotle was saying. He'd say a happy life, he's talking about a happy life. A happy life consists in, first off, meeting what he called your limited needs. You need food, you need the basic things that you need to keep on living. Because we're talking about happy life. So he says you need the right amount of what are called limited goods. Food is limited good. Too little food isn't good. Too much food isn't good. There's the right amount of food that you need. More or less than that, and you're just hurting yourself. You need the right amount of water. You need the right housing. Now, while it may vary from person to person, with each person there's a right amount. And money is another limited good. You need so much wealth. Too much is bad, too little is bad. You need the right amount. You want to question that right out the door, but think for a moment. Would you want to be responsible for every resource on planet Earth?
No.
That's the ultimate wealth. Well, that's not even the ultimate wealth. We still live as you compared to this universe. So even you, with ambitions that are probably beyond the reality that you would want, still understand that there's some cap on how much resources you would want, how much wealth you would want. You only want so much. So every human being, you have limited goods. And then you have limitless goods. And the limitless goods are developing your character, becoming a more virtuous person, obtaining virtues. Who says you can't become too honest of a person.
He says that?
Yeah. You can't be too honest. You can't be too courageous. You can't be too wise. Take the virtues. You can't be too temperate. So you can't overdevelop the virtues. And then obtaining knowledge. If you don't want to call obtaining knowledge wisdom, if you don't want to call that a virtue, depends on your position on it. So obtaining virtues and knowledge are the limitless goods. So he says you need to meet your limited goods and then get as much of the limitless goods as you possibly can. And the extent
That's his graph of happiness.
that's, well, kind of. I'm still going over a lot of details really fast, but yeah, you get those things. You get your limited goods, and you get as much of the limitless goods as you possibly can, and to the extent that you achieve those, you obtain a higher level of happiness.
Why are humans more selfish?
Why are humans more selfish?
Why are you teaching this class if all you care about is learning instead of taking the class?
Am I justified teaching this class? Is it a just thing for me to do?
No, why? Why is it just?
He's progressing.
Why is it just? Well, first off, am I doing good for you guys?
Yeah, you shouldn't care about that. You should care about your happiness.
Doing a good action is somehow a virtue. That's what a virtue is. It's doing a good action. Right? It's what a courageous person is, someone who does courageous acts. A temperate person is someone who does temperate acts. A liberal person is someone who does liberal acts. So if it's a good action, I must be cultivating some virtue. So it's a very selfish thing to do. If you want to do it that way.
Mm-hmm. Then, okay, maybe I probably won't ask this next question. We can get back on. But there is the concept of my course in life is pleasing to God, therefore I'm happy. Seems not self-centered at all.
So this kind of goes back to Edith of Rome. Conversation Socrates has with a supposedly pious man in Greece in Edith of Rome. And the conversation goes like this. He's asking Edith of Rome. He's asking what's a pious action, but you're not comfortable with that terminology probably, so.
A godly action.
Basically pleasing the gods, doing good. He says, in short, here's what he's asking. He says, is an action good because it pleases the gods, or does it please the gods because it's good?
So it's just good in and of itself.
Right. So is an action objectively good, and the gods' opinions about it are really irrelevant, but their opinions agree it's good? Or is it good by virtue of it being God's opinion that it's good?
Oh, yeah, okay, that's kind of cool. Yeah, but that's not what anyone thinks. Anyone who's always thinking, okay, I just have to please God. I need to not get on this. I need to not step too far over the line. I just need to stay on exactly how He wants me to live. So that's all they think. All they think is, what does God think me? What does God think me?
Well, I don't really care about what general people think.
Well, I'm
It's
saying
really up an argument. I don't know what you're after, but the point is.
what I'm after is no one thinks you can do good outside of what God thinks.
God loves good. He thinks good.
Is it good because God thinks it's good? Or does God think it's good because it's good? And it depends on which of those positions you decide to accept. And if you accept the latter, then it's just a coincidence that God thinks it's good. That pursuing a virtuous, happy life also is pleasing to God. Right? The other way of viewing it, and I think that this is more in tune with Christian theology. So I think Christian theology at large is of the opinion that there's no way to objectively determine if something's good or evil, and so God's standard is by definition what makes it good and evil. So they would come on the same side either from it. They would say something's good because God thinks it's good. That is what makes it good.
That's stupid because you can
Not
see,
God thinks it's good because
you
it's
can
good.
see the consequences of good. But is that I guess you think
Well-
is that society? Like if it's good to be honest, because think about a society where no one's honest, what would happen to it? Take God out of the picture. Like that argument seems easy to argue the other side.
Well, so the counter arguments to the other side, I mean, you're thinking about what would happen in a society where people are unjust, basically, right? And there's people that would make the argument that there's societies where the unjust live the happiest lives of all. And this goes back to the conversation in the Republic. So one of the people talking to Plato, or talking to Socrates in the Republic, he says, actually, injustice is a virtue. It's a good thing. It improves your lives to be unjust. And justice is not a virtue. He says, think about the thief. The thief who steals money,
Has money.
he's got the money. The poor sucker who got robbed, here he is a just dude and he got robbed. He's not going to steal that money back. Overall, he lost. Overall, the thief won. And he takes it to the extreme. He's talking about a tyrant at the time. A particular tyrant who he claims is one of the happiest men of all, who seized an entire state. He became a tyrant over that entire state. He owned all the property in the state. Everyone in the state were his slaves. He ruled the state. The guys tell Socrates, who's happier than him? It's as happy as you get, right?
No, I'm going to
He's saying
what does Socrates
just
say
are
back?
happier than unjust.
Not Socrates, someone Socrates is arguing with. So
I
the way
know.
Plato writes dialogues, you know what a dialogue is. And in Plato's dialogue, there's always Socrates talking to someone. So Socrates never wrote anything. Plato only wrote anything. Every time Plato writes, it's Socrates talking. Now, like Matthew, Mark, Luke, and John wrote about Jesus. Matthew never writes what Matthew says unless it just happens to be part of the story.
Yeah,
Similarly, Plato writes about what
Socrates said.
Socrates says. He only mentions himself occasionally if he happens to be part of the story.
Okay.
But in general, the idea you get is Plato was one of many people who followed Socrates and listened to him, but that Socrates didn't really even know Plato that well. Just happened to be another student, but student shouldn't use that word
So what's
because he wasn't formally teaching.
What is Socrates' argument?
For justice?
Yeah. Like
So the person who's arguing with him says the unjust are happier.
right.
That injustice is a virtue in that you live a better life if you're injustice to the extent that you can get away with injustice.
Right.
And one of the big arguments that they take on, so here's the big argument that they end up taking on, that someone else puts to him. He says, okay, we're going to imagine two men. The way, thinking about the times, they're saying that the two men have rings that you put on and it pretty much makes you invisible.
Okay.
So we're going to think about one man is a perfectly just man, and he has the reputation of injustice. So people hate him, people despise him, he's one of these just super unlucky people, always in the wrong place at the wrong time, always makes it look really bad. He's a perfectly just man, but he's despised by his society as unjust. And we're going to look at another man who is perfectly unjust, but has the perception of being just. He's always able to get away with it. And the story that he tells is, imagine that he has a screen that makes him go invisible, so he can go and steal things without getting caught or whatever. And the just man who has the ring would never use it, because why would you ever need to go invisible if you're living a perfectly just life? You're not trying to get away with anything. You're not trying to do anything. You're just living your life. So he paints a picture of, you're going to have this perfectly unjust man who's always going to be taking advantage of everyone around him, and he's going to get all the benefits of society thinking that you're a just man. man, so he's going to be praised as a just man, loved by his society, able to take anything he wants from his society, essentially, get away with it. So he gets all the benefits of society absolutely loving him and praising him as a just man, while all the benefits of being unjust and accumulating anything he wants. And he contrasts that with the perfectly just man, who has a reputation of complete injustice. So his society is going to despise him, hate him, ultimately rise up, torture him, kill him. Who lives a happier life?
Right.
The just man or the unjust man?
Right.
And that's the main narrative that Socrates is taking on in the Republic, arguing for the just man. And pitying that poor tyrant who gets whatever he wants and never gets caught. That poor guy.
So what's Socrates?
He never gets to experience the justice of his actions.
What's his
He
argument?
never gets to be punished.
Oh.
What's Socrates' argument?
He
Yeah.
never gets to be punished.
Well, that's not his argument. I mean, the Republic, you're talking about his biggest work.
This was it right here.
The Republic is his biggest work. Yeah, so it's probably like I don't know how long it takes to read. Have you read it before?
Started it.
It's probably like a 12-hour read, 10-hour read, somewhere around there. A solid day of
And
reading.
it's this argument, it's one argument.
And the topic of the book is justice. And it kind of escalates as they go. So first they're like, starting out with justice is, so the first they're just talking about justice, and they keep having escalating, it keeps escalating what Socrates is arguing against for the sake of justice, till it gets to that most extreme case. And when he gets to that most extreme case, he has to do a lot of work to do it. So when it's a nice simple case, he does a little bit of work to show, no, it didn't work, a little bit more, a little bit more, a little bit more, and then with this case, he has to set up a whole entire state.
Whoever is arguing with him is probably genius too. Seems like.
We have a bad, what's the word I'm looking for?
Connotation.
It has a connotation, but we have, I'm going to say definition, although that's not what I'm looking for. We have a bad definition of the word argument. Or at least it's not consistent with what a mathematician or a Greek would
What?
think
If
the word
there's a
argument.
bad guy and a good guy, what?
Well, when you say argument, you think something along the lines of contention. You think two people are opposed to each other and the goal is to be right. That's not what an argument is.
So the goal is not to be right necessarily.
No, the goal is to find the
Find
truth.
the truth.
And you construct an argument. And you and I and everyone in this room can be working to construct the same argument. So that's what we do over and over again. We start out with something that we're trying to prove. We construct an argument trying to prove it. If we think our argument's valid and it's all said and done, we say we proved it.
See, that makes me happy.
So, yeah, I always use the word argument, but when I use it, I realize I'm not communicating with people very well.
So it's
because-
not like they're against each other at all.
No, their goal is to figure out what they think is true.
So the other guy probably thinks Socrates is smarter.
Yeah, the other guy says to Socrates something along the lines of, look, I believe like you believe. I think it's better to live a just life than an unjust life. But I've never heard someone give a good argument why justice in and of itself ought to be praised over injustice. So what I'm going to do is I'm going to paint a picture of a just man who gets none of the benefits of being just, except for the fact that he's just. No other benefits. And I'm going to take an unjust man who doesn't experience any of the consequences of being unjust, except for the fact that he is unjust. And I'm going to paint this picture, and I want you to argue why it's better to be the just man than the unjust man. Because he had all these arguments in more general cases, like in your day-to-day life, is it better to be just or unjust? And he has arguments for that, but then sets up this most extreme case, and so they're building this argument.
So the most extreme is the rings.
Yeah, the one with the rings, he was using that story to help illustrate his point of how unjust this man used to be and get away with it.
Is it hard to read?
That's a hard question to
Do you
answer.
have the book, James?
It's online. All
I can show.
Plato's works and Aristotle's works,
Well,
and
audio.
So like
all these works are in the public domain.
So like, I could get it read to me, but would I want to do that?
Do you like
There's a really good reader. His name is
Bob Neufeld? He doesn't do the Republic though.
He does. I found one. I
Bob
can.
Neufeld.
Sure.
You can pull it
Is
up.
it going to be just as easy to follow an argument on audio?
Plato's arguments are pretty easy to follow because they're not dense. They're conversations. See, our arguments here are very dense. And if I were to just read the argument and wouldn't let you see it, you wouldn't understand a single proof we ever did in this class. Not a chance.
Well, it seems like these are like philosophical arguments.
Huh?
Philosophical arguments are easier to follow.
Well, in general, they're less dense. There's not as much information captured in a line, and Socrates, or Plato's dialogues, are meant to feel just like that, like an actual conversation that you're sitting there and you're a part of. And obviously, conversations you can follow. Some of the holdups you're going to have is some of the concepts that they have you're just not familiar with. So, like, they commonly would mention something like the excellence of something. You're not used to that kind of verbiage. What's the excellence of something? So,
Well, what do they mean?
well, so the excellence of something is its specific purpose, what it is that it does so well. So they would say that the excellence of a human being is their ability to logic and reason. The excellence of
Do they use the term
a
happiness?
marker is writing on the board.
Do they use the term happiness?
They're going to use the words happiness, I'm sure.
Like I'm saying, is that what they call
Well,
I guess this is all
in their mind, there's 4 virtues. The 4 virtues are temperance, courage, justice, and wisdom.
courage, temperance, courage?
But
Courage.
remember that those are our English words to capture their ideas of it. But yeah, temperance, justice, courage.
What's
wisdom.
temperance? Is it like humbleness?
No, temperance is not overindulging.
Yeah.
Oh,
This is
it's like
version 2,
being-
but
Who's that? Oh, you're sure right.
Is like
He's
so
the
temperance
reference.
is like denying myself.
Yeah, denying thyself, but I mean the most general definition I can think of for temperance is not letting pleasure dictate to your reason.
Okay.
And then the most general definition of courage I can give in their sense is not letting fear dictate to your reason, or pain is actually a better way to say it. Don't let pain dictate to your reason.
Be courageous.
That's what courage is. If pain doesn't stop you from doing what you logically think you should do, then you are courageous. If pleasure doesn't stop you from doing what you think you should do, then you are temperate. If you can figure out what you should do, then you are wise. And then if you have understanding justice, you'd have to understand his
Politics or what?
his perspective of the 3
Dude,
aspects of man. I'm not sure how to quite say it. He would break up that you have your part of your body that seeks pleasure and avoids pain. You have the part of you that is what he would call your passion, and then you have the part of you which he would call your the rational part of you. So those would be the 3 pieces of you that he would split you up into. I'm being terrible with my words right now. So I can't come up with what he calls it.
Passive.
No, those are pieces of persuasion.
Oh, yeah.
But anyways, he would say that you have these 3 principles in you. There's verbiage here. You have these 3 principles in you, and justice is having them arrayed right, with the superior ruling over the inferior, and everything doing what it ought to do.
Everything doing what it ought to do.
So his analogy with the state, he says, the just state is a state where everyone does what they ought to do, follows their excellence, in other words. So in the perfect state, the people that lead would be people who ought to be leaders, and the military would be subject to the leaders, and the shoemaker would produce shoes, and the farmer would do farm work. And the farmer shouldn't be a shoemaker, and the shoemaker shouldn't be a farmer. Now that's not a big deal if you switch those, but he says it is a big deal when the farmer decides that he's going to start writing legislation. That's when it becomes a big deal, and that's when you get a just state.
where
A just state.
justice
Now-
is not like I've sinned, now I need to have justice.
He doesn't have the simplified view of justice that we typically have of You break the law, you get punished.
Okay.
That's not good enough for him. You have to be in a state to be just. Can you do injustice even if you're not part of the state?
Yeah, can you? Oh yeah. You
By his
say you
standard,
can.
you definitely can.
So I had a purpose. He's saying I had a purpose. The minute I was conceived, I had a purpose.
You have an excellence.
An excellence.
Yes.
To go do something. How do you find that
There's
excellence?
something that you are better at than other things.
Just what you're good at.
Yeah, what by nature you do. And since you are a man, that's developing your rational mind.
So does he think that
Whereas if you were a horse, it would be different. A horse isn't rational.
human beings does he think that human beings were the perfect formula for societies? What I'm saying is, there were just enough lawyers, there were just enough shoemakers, there were just enough.
No, not necessarily. But if you have a surplus of one, you have a surplus of one. But people tend to fill into their niches pretty naturally. So, yeah, Republican. It's a great read.
I mean, go read it. What other works are by Socrates?
Oh, yes. By Plato. Remember Socrates?
I know what you're saying, but that's his argument.
He has tons of dialogues.
You prefer like a 45-minute week.
So-
if you want to start.
That if you're curious about Socrates, then there's a 4-book series that kind of covers his life. So there's Euthyphro, the Apology, Crito, and Phaedo.
What about the Republic?
Well, this is covering Socrates' life.
Oh,
I'm
so
saying
it's biography.
this is no.
Yeah.
They're all just dialogues, always conversations about some topic.
Okay.
So Euthyphro was a conversation about, is something good because God thinks it's good, or does God think it's good because it's good? But the big picture, the circumstances of Euthyphro is Socrates is showing up at a courthouse to figure out his court date. Because his society is big, a bunch of people in his society are accusing him of illegal activity. So he's going to have to go to court. So getting ready for the court date is Euthyphro. He runs into a guy by the name of Euthyphro while he's going to the courthouse or out the courthouse. I can't remember where exactly they are. Just gets in conversation with him. So that's Euthyphro. That's what their conversation happens to be about. But it's he set his court date. The apology is his trial. His part of his trial. So you don't get what people accused him of, where you don't get their speeches for what they accused him of. You only get his speech, but he mentions everything that they said, and it's him giving his defense. That's what apology used to mean. You know, we think of apology means admit guilt and say sorry. Apology is to apologize, was to give your defense. That's what it meant to apologize. Apologize. Give your defense. It's his apology. It's his defense for his action, because he's claiming he didn't do anything wrong. Crito is when he's in prison, and his rich friend by the name of Crito, his private guards, and they're there to break him out. So he gets sentenced to death. He has to stay in prison until his execution date. And a bunch of his friends break into the prison to break him out. And Crito, he's having a conversation of, I'm not justified in leaving, so I'm not going. That's,
So the big one is justice.
well, virtues are a big topic of any of his writing. And then finally, Phaedo is when he drinks the hemlock and dies.
But that's not an argument.
Well, he's with someone by the name of Phaedo, and they're having a conversation about life in general and the afterlife, and what
In
the
the
afterlife's going to be like. Yeah, in the prison. So he's the way he died is they prepared a hemlock poison for him, and he drank the hemlock. That's how you were executed, not hanging or beheading or anything. You just drink hemlock, lay down, and fall asleep and die.
What did he do?
It's just like Jesus. Disturb the peace.
Yeah, he was accused of a few things. He was accused of corrupting the youth.
Yeah, but no, that's
He
not.
was
very
accused of
common.
being an atheist.
He was accused of being an atheist.
Yeah. You got to understand, separation of church and state is a modern thing.
Right.
There was often state religion is the norm.
And he built his arguments outside of divine power.
Well, he wasn't an atheist. He was accused of being an atheist, but he wasn't an atheist. He very much believed in a god at least.
See, that's so cool.
But so those 4 dialogues, those just give you Socrates, a good feel for Socrates. Mostly the Apology, because the Apology, he kind of explains his life and what he's been doing.
That is cool.
Because his life and what he's been doing, a friend of his goes to an oracle and asks the oracle, who's the wisest man alive? And an oracle is someone who has a connection with God, right? And the oracle responds to this friend of his, Socrates. So this guy goes and tells his friend Socrates, hey, you're the wisest man alive. Socrates hears this, and in his mind, it's a riddle. Because there he is. He spent his life in the search for basically objective truth. One of the things he wanted to know is, what is good? What really is good? That's one of the things that he was always after in his life. And so, in his mind, he didn't know anything objectively good, true, or beautiful. So here he is saying, I'm not wise. And yet, you're telling me that the oracle said I'm the wisest man alive. So I'm going to go put this to the test. I am going to go find someone wiser than me. And that's what he spends his time doing. So he goes to the poets, and he goes amongst the wisest of the poets. He listens to what they have to say, and he points out that they're really not that wise.
So yeah, as people are.
They get mad. He goes on to the politicians, speaks to the wisest of them, points out to them, you're really not that wise. They get mad. Goes on to the artisans, speaks to the wisest of them. And in every case, he thinks he's slightly in the superior to him. Because here they are. He knows nothing, and he doesn't think he knows anything. They know nothing, but they think they know something. So he thinks he has a slight advantage on him. Because he at least knows that he doesn't know.
So he literally, the conclusion he came to in his life was, there is no truth, wisdom, or beauty.
No, he absolutely believes in objective good, objective truth, and objective beauty. His conclusion would be along the lines of, none is wise but God. And compared to him, we're nothing. We don't even know anything objectively good. We can't name one thing objectively good. And so we're so limited. So he'd say that none is wise but God. And what was the other piece I was going to say? What did you say?
I said, so the conclusion he came to was, there's no beauty, wisdom.
Oh, right. And that's what made me lose my train of thought, because I was going to say something when you said that. He believed that you spend your life, he believed in objective truth, objective good, and objective beauty.
Objective means
And-
entertainer, right?
No, objective meaning it's not subjective. In other words, your opinion about what's true is irrelevant. It's true or it's not.
Okay.
Your opinion about what's good is irrelevant, it's good or it's not. Your opinion about what's beautiful is irrelevant. It's beautiful or
Why
it's
do you
not.
say I'm objectifying women? That means like they're an object and I can obtain them. That's what that means.
Okay.
Okay. If that's
Well,
objective.
there is object in that sense, but the reason that we say object for something in the real world is it's implying that there is some objective reality. So some people think there's no objective reality. There's just your perception, and you just have your perception. There's no real reality out there. But the reason that we call this an object is because we're both agreeing that even though I have my perception and you have your perception, we both agree that there's an objective world and here's an object in it that we can both experience. So if you can perceive it and I can perceive it, it's objective. It's an object. So he believed in objective truth, objective morality, and objective beauty very much. And he spent his life in pursuit of what he would call the good, the true, and the beautiful. That's what he would call wisdom. Knowledge of the good, the true, and the beautiful. I still can't remember the train of thought I was on before.
So where am I going to find the Republic? It's just one of his works.
It's just one of his works. He's got dozens upon dozens of dialogues.
Really?
I've probably read like 30 of them. I don't know. Read a lot.
You wouldn't regret any of those reads.
I have a book, and Martha now has it, but she hasn't given it back to me. But it's called The Essential Dialogues of Plato. And it's a big 1,500 page book.
words, or is it like
It's his works, but it's also got commentary as it goes. And sometimes the commentary is good, sometimes it's pretty useless.
Yeah, I like page Roberts.
Uh,
Is it like, will the author be like, when he says essential, then this way I can use?
So in
Or
the,
excellent sentence.
in the Essential Dialogues of Plato, then kind of they go over like a 10,000-mile view of the argument. So they go over the setting, so that you know what the setting is. They'll probably go over some basic Greek ideas that might be brought up in the dialogue. And then they'll go over the argument for you in plain English, in modern vocabulary, modern terminology. And then you'll read Plato's version of it, the exact words. So you do that at the start of each of the dialogues.
Useful?
Sometimes, sometimes not. I mean, it's kind of weird when I feel like I'm reading, I read what they have to say and I just have to say that's so false. That's not what he's saying. Like, one of the stupidest ones is, so one of the things Socrates often talks about is an internal oracle. What's his internal oracle? It's his conscience. That's what his internal oracle is, his conscience. And so he says this voice inside his head that warns him not to do bad things.
The author thinks it's divine intervention.
No, but I don't remember if it was the author, but it's a common thing, for example, that people say, oh, he was a schizophrenic, he heard voices. No, that's not what he's talking about. And if you read his works, it's obvious that's not what he's talking about. He didn't have this external voice always talking about, thinking, oh, there's someone right there, there's someone right there. Talking about an internal oracle, an internal voice of truth, and what we would call the conscience. So, the stupidity of some of it, if you read his works, I just find out, I mean, maybe they're right. There's no way to know for sure. But I feel like a lot of the time their commentary is very inconsistent with Socrates, especially when I know a lot of them, when I go and read some other dialogue, I listen to their commentary, I have so much to fall back on.
What's the book called?
The one I have is called The Essential Dialogues of Plato, but you could I also just have the Dialogues of Plato,
Let me go steal that one from Martha.
you should give it to me. I think she has it. I should say. She for sure does.
Just go steal that back from me.
She goes steal it so I can do the borrow right now.
Sure, if you're going to return it when you're done. And if you can actually use it.
Well,
I'm all for people using a book. I hate a book going to waste.
That it's a great work from
what's your word?
which has Plato.
Yeah, it's not going to have all Plato's works. It's going to have what we're deeming the essential ones.
And Plato's works means Socrates, right?
They're about Socrates.
Some
Oh crap.
Is it a series?
And my other question is, how's Plato write that crap down? Because
he goes and talks to people. That's how I see it.
What do you mean? How
Either
does he
he's
write
not
it?
there, and he
24
talks to someone, or he's
dialogues
there.
is what we have.
of Socrates.
Yeah, of Plato's.
Okay, yeah. So there's no way Plato was literally taking minutes of conversations because you couldn't. He must have understood the argument very well.
Yeah, it's very well, it's somewhat understood that a lot of it was Plato. So
Okay.
some of it is Plato's original stuff, using Socrates as a medium to communicate the information. I thought I came across something saying that Plato had more rigorous texts, and we just don't have them today.
They were lost at the academy.
I don't know if they were lost in the fire in Alexandria,
Yeah.
or if they were just lost in general, but I think I've heard stuff along those lines, because I know I've also heard stuff along the lines of, we think that the works of Aristotle that he has weren't his complete works, but they were typically notes for his complete works, because they're very dense. When you're reading Aristotle, it's very dense. Reading Aristotle and reading Plato are not close to the same thing.
Why would we have their notes but not their book?
Well, it's just, I mean, what's preserved is kind of random. You get some, you don't get some. So we're missing tons of works from past people. We don't know what the body of knowledge
Gives
was.
me an appreciation for God, having people keep records and preserving them in plates. Like, there's logic behind that.
It's hilarious though how many libraries
Jeez.
were down.
We did not even start the next section.
Gosh, Jake. No, I'm gonna have to go cut off like.
No,
Don't